Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello again. Thank you for choosing IT Pro TV, helping you learn everywhere you go. I'm your host, Zach Memis, as we continue on with compTIA Net Plus, and this is Network Traffic Properties Part 2. And Part 1 was great, but Part 2 is going to be even better, I'm telling you. And Wes Bryant is here to give us all the information we need. Wes, good to see you again.
Hey, Zach, thanks for having me back. Having a lot of fun, that's right. And there are some more characteristics, or just like Zach said, more properties that we need to be aware of when it comes to your network communications. Now, if you didn't check out Part 1, definitely go check that out, because it's really going to set the stage for some of the concepts that we're going to talk about in this episode. We talk about the communication types, unicast, broadcast, as well as multicast. And then we talked a little bit about the difference between a broadcast domain and a collision domain, right? And that's going to set us up for some additional properties or characteristics that we need to be aware of. And the very first one that I'd like to talk about is a whole bunch of alphabet soup right off the bat here. So let's see if we can help you out with this one. This is CSMA-CD. All right, so what the heck does that mean? I can see Zach over there.
Let me officially ask it. What the heck does that mean?
I can see Zach going, oh my gosh, what is that? That is carrier sense multiple access collision detection. And what we mean now, let's just step back for a second and do like we like to do here at Net Plus, if this is the first time, and even in A Plus, is break down these acronyms and kind of look at each individual word here, right? So we can kind of get a grasp of what's going on. Carrier sense. All right, well, what's the carrier? The carrier is essentially the network, right? Carrier sense, if you will, it's sensing, is the network available? Multiple access, and I might have said media access, because we got to be careful with that. It's carrier sense multiple, if I did. Multiple access is what it's supposed to be. So think of it, carrier sense, can we sense the network, and multiple access, more than one node accessing the network. And then the last part, CD, collision detection. Remember, one of the things that I told you is that in the first part of this episode, I said that, if you have computers that are on the same Ethernet-based network, then there is because it's a contention-based media access, right? Again, we have multiple computers striving to send their information, contending, if you will, competing to send their information out over the wire. The collision detection part is that they can be made aware. One of the things that I also said is that the connectivity devices don't have to have a lot more logic in them, just because the devices themselves can kind of duke it out and battle it out, and that's what kind of brought the price point for Ethernet communications compared to deterministic media down, which is also one of the reasons that it became so popular, right? Now, how do they do that? When we say carrier sense, multiple access, collision detection, how does that process work? Well, let's go ahead and let's take you through a few steps here that I've got kind of laid out for you, and we'll take a look at that, all right? So we got a couple of computers here. Carrier sense, what are they doing? I am listening, and do we see data? I don't know why I got a question mark there, but I am listening. No data is being transmitted, right? First you got to sense, is the media there? Is it even available, right? That's where we get things like our link lights on our adapters, right? You plug it in, there's a link light. You don't have to have activity. That doesn't mean, if you have no activity, it means you're not sending any information, but the link light's there. We can sense that the media is available. Well, I'm listening out. Is there data being transmitted? Well, I don't hear anything. Well, you know what? There could be another computer doing the same thing. And again, I don't know why I got the question marks in there, so we'll fix our slide on the fly, because that never goes wrong, right? I'm listening, and I don't hear that there's any data being transmitted. So guess what? We're going to go ahead, and first computer says, I'm going to transmit my information. Guess what happens to the second computer? The second computer says, I'm going to transmit my information. Well, now we've got a problem. Remember, when we've got two computers that are sending information across the same shared medium at the same time, this is where we get a collision. Now, here's something that's kind of, I want to say magical. Nothing in computing is magical. Nothing in computing happens unless they program it that way. Nothing is magical, right? I don't care what Steve Jobs says, right? This is actually kind of the cool part, right? And this is the fact that when the collision is detected, you say, well, wait a second, Wes, how is the collision detected? Well, remember, we send communications down the same, electrical communication down the same shared medium. It's going to collide, and it's going to bounce back to the sources of the communication. in the form of a fragmented frame. And they're going to see that. They're going to detect that. Hence why we call it collision detection. They're going to detect that, and what they're going to do is they're going to wait a random back-off period. Now, I know it's programmed in there somehow. I don't exactly know what the back-off period is, and understand we're not in an electrical or a network engineering class here. We're taking a Net Plus exam. They're not going to want you to know that, but just understand they wait a back-off period, right? And once that back-off period is reached, they retransmit their information. Now, what happens is if they wait a back-off period, right? They randomize it to try to make sure, and it's pseudo-random. They pseudo-randomize it so that we don't send it at the same time, all right? Well, if it happens, which it can, if it happens again, they're going to adjust that back-off time. And right, they keep adjusting that back-off time. And the thought process is if you have two trains going down the same tracks, it's kind of like when they switch the gates open, right, and they kind of veer off to the side there, right? We're hoping that the tracks have switched, right, and we've got a side rail here. Basically, what's going on is they're trying to eliminate those collisions. Now, that's collision detection. We see that this media access method, and it's inside of your Ethernet-based networks. Now, today, I do want you to understand that every computer is plugged into a switch today. We've pretty much eliminated the hubs. However, I want you to know that we still have collisions. And how can we have collisions? Because they're broadcast communications that can happen. The more broadcast communications you have, the more potential there is for a collision to happen. It just happens. So don't think that you eliminate it altogether, but it is greatly reduced because of the fact that, again, each computer now is on its own collision domain, but it doesn't mean that they're on their own, they're still within a broadcast domain like we talked about in the first episode. So do know that. Know that this is associated with 802.3. Remember, 802.3 is the IEEE's formal standardization for the Ethernet, technology, and then all of its amendments and derivatives thereafter. All right? So that's how we do it on a wired network. The next one we got to talk about is in a wireless communication, right? Wireless communications, remember, are unbounded media, right? We do not have the bonds of a physical cable, all right? So we have some good things and we have some bad things, right? One of the good things is when you have the limitations of your physical cabling, you can go to wireless, right? And you can get around that. One of the bad things is that when a collision happens, it doesn't bounce back to the source. It's not a shared cable, right? So we can't really detect whether a collision has happened. So collision, CSMA-CD, or collision detection, doesn't work in a wireless network. So what they did is they came up with another type of CSMA, still the same thing on the first part, guys and gals out there. Don't let that fool you, carrier sense multiple access. But now it's CA, it's collision avoidance. All right, now, let me be very clear on this one. The goal is collision avoidance, right? That's how Zach and I drive to work in the morning trying to get here to our job, where our goal is to try to avoid a collision, but on the way into work, you see people that unfortunately have collided, right? So the goal is to avoid collisions, right? So let's talk a little bit about CSMA-CA. CSMA-CA. Make sure I get that acronym right. Carrier sense multiple access collision avoidance. Let's go ahead and take a look at our diagram here. Now, it's a little bit different here. All right, so we still have a carrier sense, and I could say that, hey, is the media present, right? You still have that carrier sense that has to go on. Is the network there? Is the media present? In this case, the media is unbounded radiated energy, but the network's there, right? And when a device senses that media and senses that it's there, it signals its intent to the rest of the network and says, I've got information to send. That's a form of, in the form of what's known as a jam signal. All right, and the other computer that's within earshot says, oh yeah, I heard that. You've got data to send. It'd be like Zach saying, raising his hand in class if we were in class together. Oh yeah, Zach, okay, you've got something to say? Everybody else, hold off for a second, including the teacher or whoever, is in the front of the class at that time. Just hold on. Zach has the floor, right? That's kind of how the jam signal works, right? And then the data is going to be transmitted, all right? Now, here is the thing that can happen, all right? Here's one of the reasons I say the goal is collision avoidance, all right? Because let's take it. I tell you what, we're going to use this analogy. Zach, you and I, we go out to Ben Griffin Stadium here in Gainesville, right? And we're standing literally on the football field, right? I'm on one side of the 100 yards, you're on the other side of the 100 yards. We're both in the end zones or whatever on the opposite sides of the field. I want you to imagine that we have somebody right in the middle of the field. We represent these devices here, client 1 and client 2. All right, the person that's in the middle of the field represents the access point, okay? Now, there is a good chance that if I was on one side of the field and Zach was on the other side of the field and I said, hey, Zach, I've got information I got to send, that Zach wouldn't be in earshot and couldn't hear me say, I have data to send. Just like on the other side of the field, I didn't hear Zach say, I have data to send. Nobody's seen us raise our hands, right? We're too far away from each other to hear that. So we both send information at the same time. And a collision happens. But here's the problem. There's no way to detect it. It doesn't bounce back. It just, whatever it does, goes off into electrical limbo, right? It's gone. So we're having collisions. Again, the goal is to avoid collisions, but it doesn't mean that it wouldn't happen. So they knew that. They knew that there was a potential. What this does is it creates what's known as a hidden node phenomenon, and that's where there's a node out there saying, I've got information, sending a jam signal. Nobody can hear him or her, whatever, you know. All right, nobody can hear that device. All right. So what they did is they came up, say again, no detection of a collision. We think everything's good, right? We can't detect it. We think everything's good. And so they came up with a kind of a way to try to get around this hidden node syndrome. And that's something known as a RTS, RTS-CTS signal. All right, now, again, I know another acronym, and I'm not sure if they're going to ask you this on the exam, but if they do, you'll be prepared for it, right? So what does a RTS-CTS signal stand for? Well, RTS is request to send. Let's go back to the analogy of being on the 100-yard, on a football field. All right. Now imagine, Zach can't hear me communicating, saying, hey, I've got data to send, or hey, network, I've got data to send, and I can't, for whatever reason, I can't hear Zach saying, hey, network, I've got data to send. But wouldn't it be nice if we could talk to the person that's sitting right in the middle of the field and say, hey, anybody else sending information? I need to send some information. Because the person in the middle of the field can hear Zach, and the person in the middle of the field can hear me. We can't hear each other, but if I ask that person, hey, can I talk? And that person says, Zach's talking right now. Oh, okay, I'm not clear to send. I got to hold off for a second. And then I request to transmit again, right? And then finally the access point of the person in the middle says, yeah, I can hear Zach. Zach's okay. The network's quiet. Go ahead and send. And what it does is it says, hey, Zach, Wes is sending information. You need to stop right now. Just hold off. All right, he's got his hand raised in the classroom. And it sends me back the CTS signal that says clear to send. You're clear to transmit your information. So request to send, clear to send. Or request to send, hold your horses, somebody else is sending, however it might work. And that kind of helps to eliminate or to combat that hidden node syndrome. That is carrier sense multiple access collision avoidance. The goal is to avoid collisions. Now, I'm going to get a little bit specific here, specifications, technical jargon. Know that that's for your 802.11 networks, just in case they ask you on the exam. Where do we see CSMA-CA? We see that in our wireless networks. Remember the IEEE's formal standardization of wireless communications, wireless local area network communications, is 802.11. Remember that your CSMA-CD collision detection is what the 802.3 or Ethernet-based wired networks use, all right? And it is important to understand the 802 designations. And the reason I say that is because you have to learn the jargon. I don't know, I couldn't tell you which question they're going to give you on the exam. I'm not sure. So if you understand the concepts, you understand that that's associated with Ethernet, and by association you know that Ethernet is 802.3, they might give you a question that says, which of these media access methods is, does 802.3 use? And you have to say, well, I know 802.3 is Ethernet, and I know Ethernet uses collision detection. So you see how it's more of those pieces of the puzzle, and it's going to help you do pretty good on the exam if you can start to put more of these concepts. I understand that when you look at the objectives, it's like somebody taking a 10,000 piece jigsaw puzzle and throwing it on the table, and you got to try to make some sense out of it. Well, you don't have to understand the whole picture right away, right? You don't even have to know what the picture is, but you can start to flip over the individual pieces, and then we can help you put those pieces together so you can sit back and look and realize, oh, that picture's a network. And this is what we do to put it together, right? So we do have to know some of those individual pieces. All right, now we've got some other things that we need to be aware of too, and one of the things that we have to be aware of is what are known as PDUs. All right, when we talk about a PDU is a protocol data unit, and it is important to understand what protocol data units are, PDUs. Now, this goes right back to our OSI model, and so you do have to know, again, I say sometimes we're trying to steer away from those theory concepts, but you're going to see more and more that OSI model just keeps creeping up. It never seems to go away, and it always seems to come back. So with a protocol data unit, I want you to think of, well, a couple of things, all right? One of the things I want you to think of is, again, that OSI model. And when we look at the OSI model, you'll remember, and in fact, I've got my slide here up. Let's look at the OSI model rather than just sit here and talk about it. You remember the OSI model, and if you haven't seen that episode, check the OSI model out because it's important. Remember, we have the different layers. We've talked about the different devices that operate at the different layers, and then we also talked about encapsulation. All right, well, encapsulation is really a upper level service, right, layer, handing its information down to a lower layer, and that lower layer puts it and wraps it in that container, right? Kind of like the onion peels that we talked about in that episode, or those Russian dolls, right? A smaller doll is put into a larger container, finally until you got one big doll. Well, a protocol data unit is, let's take the session, let's take the session layer here, right? So the session layer is going to require the services of the transport layer, right? We have our physical data link network transport session, right? Well, when that session layer is done with the information that it's encapsulating from the higher layers, it creates what's known as an SDU. That's a service data unit. It means I've got my data. Session layer, I'm done with what I need to do, and now I need to send my information down and rely on the transport layer to do its job. So it's requesting the service of a lower layer. That's how the OSI model works, right? Well, when it passes down its service data unit, the transport header encapsulates it, right? It adds its bit of information, basically doing its job. Well, that becomes what's known as the transport layer's PDU, a protocol data unit, all right? So it receives from an upper layer, and this is how it works. It receives the service data unit from the session layer. It does its job, it encapsulates it, and that becomes its protocol data unit. But now it needs to rely on the layer before it. So now it's going to require the services of a lower layer. And what it's going to do now is it has its own SDU, because it says, hey, my protocol data unit is here. I've added my information, and now I need to send this down to the network layer. And when it does, it requests the services of the lower layer. That's a service data unit. Now, when the network, and you can kind of see that this just keeps happening, right? Now that the service data unit, it's going to be passed down, if you will, from the transport layer to the network layer, and the network layer is going to put its information, encapsulate its information on the transport layer's data, and that becomes, well, the network layer's PDU. Now that it's prepared its information, it's done its job, it's going to rely on the services of a lower layer, so now it has its SDU. It says, hey, I've got my information, my PDU, my protocol data units there. Now I'm requiring the services of the layer below me, so here's my service data unit, and it keeps doing that, and it goes down the stack. All right? Now, and that's what they mean by going down the stack. You can see how these layers stack on each other. Now, the last thing that happens, right, well, second to last thing that happens is that the data link layer, what does it do? It encapsulates the entire stack's information into a frame. That's why we talk about switches. They work with frames, right? So the frame now is the data link's PDU. And then the data link layer, and more specifically, through that MAC sublayer of the data link layer, I know this gets confusing, hopefully it's making a little sense here, says, all right, now I'm ready to put the information out on the physical wire. So at the physical wire, or at the physical layer, last layer of the OSI model, we get its PDU, all right? Now, what are the PDUs? They have names, and I want you to be aware of that. So let's go ahead. I got a little diagram here, and I want you to know the different protocol data units, all right? Now, I've got a little mnemonic that'll help you. We'll talk about this mnemonic here in a second, so don't worry about it. The protocol units are not called Some People Fear Birthdays. We'll get there in a second. That's a little mnemonic.
I fear birthdays all the time.
We fear birthdays as we get older, Zach, right? So let's look at the layers, right? So when we talk about layers 5 through 7, it's just called data, because at this point, remember, that's the application block, and it's just preparing your data to put on the network so we can start to move it. So it's not until you get to layer 4 that they start to talk about the PDUs. Again, the protocol data unit for anything above that's just called data. But I want you to think about what is happening at layer 4. Transmission control protocol is starting to segment your data and do sequencing, right? Well, protocol data unit, that encapsulation, when the transport layer receives it, it encapsulates it into a segment. That's its protocol data unit. Now, when it's done its job, and it's finished its job, and now it needs the services of the network layer, it takes its service data unit, and it basically sends all of that encapsulated information down to the next layer. And the next layer wraps it in a packet, and that's layer 3. The network layer, if you will, its PDU is going to be a packet. Then we get down to the data link layer where our switches operate, right? And the data link layer encapsulates everything in a frame. That's its protocol data unit. Last but not least, at the physical layer, this is where we get the raw electrical pulses, right? We get the bits, the binary bits, ones and zeros. So at layer 1 of the physical layer of the OSI model, we have what's known as just a bit, all right? So those are the 4. You could say 5 if you want to talk about data itself, but I wouldn't worry about that. I never want to say that. I got to stop saying that. Always worry about it, but if you can remember data from 5 through 7, you'll be doing good. Now, to remember the other ones, 4 to 1, use the mnemonic. Some people fear birthdays, right?
I see the gist of your jib there.
There we go. And it'll make it a little bit easier, right, if you need to remember, which one is which on the exam, all right? So know your protocol data units, right? Okay. Now, the last thing I have to talk about is what is known as an MTU, all right? And when we talk about an MTU, that's a very important characteristic or property of your network communications. That is called a maximum transmission unit, all right? I want you to think about, let's think about we're flying in an airplane, right? I said that I was going to take 2 bags. When I show up to the airport, I have 5 bags. We're not going to say that you could pay more money and you could bring those bags. What would you have to do if you said, hey, I'm not going to pay any more money for those bags?
Leave them.
You've got to leave them, right? You drop them off.
That's right.
Well, an MTU kind of works like that in the fact that a maximum transmission unit is defined by the maximum amount of information that can be in a single frame across an Ethernet link and across the network, right? How do we know what the MTU is? Well, your operating system typically sets the maximum transmission unit, and then it's your system administrators, your network administrators that set the MTU, maximum transmission unit for a link, on the connectivity device itself. For different scenarios require different MTUs, but I want you to know for your exam, the default MTU on an Ethernet network or an Ethernet-based network is going to be 1,500 bytes. All right. Now, there are scenarios where that changes. When you get over into some of the other episodes that Zach and I have recorded here in Network Plus, you're going to learn about jumbo frames, right, where you can increase the MTU up to 9,000 bytes. All right. There's goods and there's bads with that, right? I want you to think about it. If I have 1,500 bytes, I receive 1,500, all right? I have to check inspect, because it gets a little redundant. I have to inspect a frame checksum sequence. I have to check a frame checksum sequence, right?
Check that checksum.
That's right. Got to check that checksum. So the FCS is at the end of the frame. Remember how our switches typically work. Most common is a store and forward. Receive the whole entire frame. Inspect, if you will, the FCS, the frame checksum sequence, which is just a little CRC32 value, cyclic redundancy check. And if we inspect it and the frame has maintained its integrity, then the switch forwards it on. That's why they call it store and forward. All right, now, if I inspect 1,500 bytes, then 1,500 bytes, then 1,500 bytes, versus 9,000 bytes all at one time. Well, you might say, well, wait a second, I can see where jumbo frames might increase the speed of your network. Yes, they could. But I also want you to think about what if the frame checksum sequence on a 9,000 byte frame is checked and there's one bit that's bad in it. An entire 9,000 bytes is thrown out versus 1,500 bytes being thrown out and just resend that 1,500 bytes. So it does have the potential to speed up your network, but it also means you're going to throw a lot more information away if there's an error. So again, it's always a give and take. There are other scenarios too, and this goes well beyond the exam and the focus of the scope of this exam, but you'll learn as you go on to other advanced training, like for instance in configuring DNSSEC, right? DNS security, right? A standard UDP DNS query, like we talk about in DNS when I need a name resolution, I have a name, I need what's the IP address, and I send that query out to a DNS server, that's 512 bytes. Well under the MTU, no problem, right? If you're using DNSSEC, you could have a response that comes back from the server that's up to 4,096 bytes, which means that could cause you problems. It's like that packet being, or that frame, excuse me, being delivered back to you, and it hits the connectivity device, and it's like the airport. You got extra bags. You're not paying for them. Guess what we're going to do? We're going to throw it out. So you need to understand what the MTU is. Now, I will tell you, in fact, let's go ahead and dive back into our Windows machine here, and let me log back in. It looks like I timed out. And you can actually see this. Another command, and I don't see this command much in the objectives, but I will throw it out there just in case they ask you about it. It's called network shell. We call it NetSH, net shell. It's the way you can interact with the network stack inside of Windows. So you can do a NetSH, you do interface, and IPv4 show interface, and we can actually see that the operating system is setting the MTU, right? So the MTU is set by the operating system, and then it's peaked and tweaked according to whatever the administrator wants across the switch or across that link itself. So there are other occasions where you might exceed as far as the connectivity device goes. In your networks, you might exceed the 1,500 byte MTU, and that's when we talk about VLANs, because VLANs adds a tagging unit to it that could potentially grow that just beyond 1,500 bytes. You'll learn more about that as you go on to things like Cisco training. There's another way that you could look at. You could run that also, and instead of doing interface, if you wanted, you could do sub-interface. And it just kind of rearranges it a little bit different, but you can see that it's 1,500 bytes, right? I tell you what, we'll do another one here. Let me go ahead and bring up my terminal on the Mac OS here, and you all can see that one likewise too. So if we do an if config, all right, and I'll just do a -A, you can see that if I scroll back up here, we've got 1,500 bytes right there. So you can see there's the MTUs. 1,500. Some of these different like wireless networks and even this P2P here, you can see sets it a little bit different. But for the main part, your Ethernet-based adapters, they're going to have your 1,500 bytes. So you can see that that's something that is set inside of the operating system. But then ultimately across that link, it'll be something that is controlled by the network administrator themselves. So these are some of the properties of our network traffic that you need to be aware of. And as you can see, as we've gone through a couple of parts, it's not really just about what's on the exam. It's really about knowing the DNA of the communications as they traverse your networks, and where you might see some of these, and in the scenarios that you might want to eliminate these, like broadcast communications, reducing collisions on your network, shortening collision domains by using switches, getting the hubs off there. So not only for the Network Plus exam, but also for your own experience in networking in the real world.
Great job as usual, Wes. Thank you very much. Network traffic Properties Part 2. There was a Part 1. See them both and see everything inside the compTIA Net Plus series that Wes has put together for you and done such a fantastic job at getting all that information we need for those exams and so forth. And by the way, when you're inside the course library, there's hundreds of other videos. They're all designed to help you go further, so check those out. And tell everybody you know about IT Pro TV. They'll be very glad you did. Thanks for watching. I'm Zach Memis.
And I'm Wes Bryant.
And we'll see you soon.
Thank you for watching IT Pro TV.